Hi everyone, this is Zijian from Cactus Lab at Arizona State University. Today I will present our paper, Integration of Fast Evolving Data Sources using a Deep Learning Approach. It's well known that 80% to 90% of a data scientist's time is spent on the data integration and the wrangling process. The industry urgently demands an end-to-end pipeline that can automate this process and reduce the amount of human efforts involved in various data science applications. In this work, we focus on the automatic integration of fast-evolving data sources and try to answer several questions. How does data evolve? How does data evolution affect data integration? How to integrate fast-evolving data without human intervention? Taking a data analytics task, COVID-19 outbreak prediction as example. This requires the right set table that contains time, location, coronavirus, and mobility information, which can be integrated from the Johns Hopkins University's dataset and the Google Mobility dataset. However, we observe that both datasets evolve frequently over time. Taking the GH2 COVID-19 dataset as an example, we observe that the database design, like the number of tables, changes at the daily basis in the first month. In addition, in the following months, new attributes get added, while some of the existing attributes get removed. According to the common history of their GitHub repository, we observe even more schema changes and value format updates. Because of such frequent updates and evolution, someone even manually maintain a clean version of the GH2 COVID-19 data, which, of course, requires huge human efforts. We have observed that most data evolutions can be categorized into 4 types: dimension pivoting, non-key attribute addition or removal, changes in attribute name and value formats, and key expansion. We will describe these types one by one using real-world examples. Dimension pivoting is a well-known schema change, observed not only in coronavirus data, but also in many other data sources, such as the National Oceanic and Atmospheric Administration climate datasets. It means that a subset of the attributes, such as the March 20th, 2020, March 21st, 2020, in the left table, are pivoted into values of a single attribute, like the date in the right table. For the case of non-key attribute addition or removal, new attributes are added or existing attributes are removed. In this example, the dataset is changed by adding 2 new columns, latitude and longitude. The third type of data evolution includes the changes in attribute name and value formats. For example, like the abbreviation name to full name, and another slight changes in attribute name, such as the underscore to slash, which is shown in this real-world example. Another evolution type is called key expansion. In this example, where the 2 attribute composite key of the left table, which uniquely specifies the state, is flattened into the 4 attribute composite key, shown in the right table, so that each row describes the information regarding a county. Besides COVID-19, data evolutions are also ubiquitously in many other scenarios. For example, in the Internet of Things scenario, sensor devices with different manufacturers and models may use heterogeneous formats to describe data. In addition, in a machine log merge scenario, logs collected in different types of machines at different times may have inconsistent formats. Each time data evolves, it may break the data integration pipeline, and the programmer have to spend time in debugging and fixing the problem, which may take a lot of expensive manual efforts and cause delays and interruptions to the data integration and analytics process. To avoid these interruptions and save human resource costs, we propose to train a deep learning model that maps each data from the user-specified data sources into its position in the target table. The training data is prepared using a special approach so that potential data evolution are automatically injected. We will describe them in details later. In the inference process, even if source data are evolved and use formats that are different with the initial state, our deep learning-based integration pipeline can still correctly map each data item to its position in the outcome table. There are many two ideas behind our approach. Firstly, we use a key value representation to model data items in data sources, so that the key is the context that describes the value. Then we can decompose the raw data sources into sets of key value pairs. The benefit of this representation is that now the integration decision is made at the cell level, which is the most fine-grained level. Then we can avoid the fuzzy join and reunion problems caused by attribute-level integration. Second, we automatically inject data evolutions when constructing the training data so that the model can recognize and handle various types of data evolutions. Next, we will describe these two ideas in details respectively. Here, we give an example of the key value-based data representation. For each cell value in the CSV file, it can be transformed into a quadruple that includes key vector, key type vector, value, and value type, where the key includes attribute name of the cell and the row key of the cell. For example, the value 1 and 3 in the up table is represented like this and this correspondingly, and the value 126 and 1 in the lower table is represented as this respectively. Now, we describe how we augment the training data to handle various schema evolutions. With our key value data representation, both of the dimension pivoting and attribute addition or removal can be naturally handled. For example, the time series COVID-19 tables are refactored into a set of tables with dimension pivoting, where each table describes information regarding a specific date. However, as you see in the middle of the picture, the key value representation of cells from the two different data sources are similar. So naturally, in the inference process, each cell will be mapped to the correct position. To seamlessly handle the evolutions in attribute names and value formats, we further utilize word embedding to represent the text values so that semantically related words are assigned with close embedding vectors. In addition, we automatically augment the training data by replacing words using synonyms extracted from the Google Knowledge Graph to better handle similar words. Next, we will describe these approaches in more detail. We tried various pre-training word embeddings, including word2vec, which was pre-trained with Wikipedia corpus, and another approach known as fast text. Because in our data source, a lot of the text-based attributes names and cell values are customized abbreviations and out of the vocabulary. The character-based embedding, like fast text, has a better performance for our test cases. Google Knowledge Graph is a widely used tool for entity matching. In this work, we utilize it to extract synonyms to replace words and augment the training data, so that we can improve the model to have an even better understanding of similar contexts. To handle the data evolution type of key expansion changes, we augment the training data by injecting hierarchical relationship. For example, a country contains multiple states, and a state contains multiple counties. So once we detect attributes such as state, we will automatically inject training data at a lower level, such as county. More details can be found in our paper. We implement the prototype using Python and TensorFlow. We test our prototype on a computer installed with Intel i7 processor, 32 GB memory, and NVIDIA GPU processor. In this work, we mainly evaluate with two scenarios. The first one is COVID-19 death case prediction. We use two datasets from Castle Health News and Harvard University to integrate attributes such as population, death cases, number of hospitals, ICU beds, and so on. Here, the Harvard COVID-19 is a white table and has 459 attributes. For the second scenario, we integrate data for COVID-19 confirmed case prediction using two datasets collected from Johns Hopkins University and Google. The target attributes to integrate it include geological information, confirmed cases, various mobility factors, and so on. We compare our proposed deep learning approach to a baseline approach that utilizes locality-sensitive hashing, which estimates the similarity between two attributes. We mainly compare with four metrics, including accuracy, storage overhead, latency, and productivity. For the baseline approach, the main idea is to apply a family of meanwhile hash functions to create a set of signatures on each attribute, and split each signature into multiple buckets, and store each bucket of signatures into a hash table corresponding to the bucket. We also create signatures similarly for query attributes, which are then used to query the hash tables. Once similar attributes are identified, a manual process is required to perform a joining operation of the two tables on the matching attributes. Then, the different tables are integrated together. For accuracy, we observe that our deep learning approach can well adapt to a lot of data evolution scenarios, where the baseline approach cannot handle the dimension pivoting changes and fail with evolved data sources. We test with two different model architectures and find that the convolutional neural network can perform better than long short-term memory in most of the cases, since CNN considers the locality of features. For storage overhead, we observe that the deep learning approach can save about 100 times storage spaces, since it requires storage size only related with the number of model parameters. But for baseline approach, the storage size will linearly increase with number of attributes and updates in attributes. Also, we surprisingly find that the proposed deep learning approach can achieve comparable latency with the baseline approach and performs even better for white table. Most importantly, our proposed approach can provide better productivities as no human intervention is required to handle data evolutions. In contrary, the baseline approach needs manual efforts to handle dimension pivoting and to discover the join or unit schemes, which interrupts the automatic data integration pipeline from time to time. In this paper, we identify and focus on the problem of automatic integration of fast-evolving data sources. We propose a deep learning approach to address this challenge, which contains many two ideas: a key value-based representation for decomposing raw data sources, and the automatic injection of various data evolutions to augment training data. Through our evaluation on two COVID-19 data integration scenarios, we showed that compared to our LSH-based baseline approach, our deep learning approach can provide better results in accuracy, storage overhead, latency, and productivity. Our work benefits a lot from related works in three areas. Existing works in data discovery aim to find related tables in a data lake, while most of these works are matching data at the level of attributes. We do it differently and match data at the cell level, utilizing a key value representation in quadruples. And there are also a lot of works in the area of entity matching that introduces various distributed and local representation for texts, which we can also leverage to improve the accuracy of our work. Finally, there are a bunch of works regarding handling schema evolution in relational databases as a query discovery process by searching for queries that may transform the source schemas into target schemas. However, our approach can also handle heterogeneous data sources that may not have schema explicitly defined and can handle more types of data evolutions. In the future, we will explore transfer learning and crowdsourcing to further reduce the human efforts required in the training data preparation process. Also, we will enhance the framework to scale it to more heterogeneous datasets like JSON files and text files. We will also evaluate our proposed approach in more real-world scenarios. Thanks for your attention, and we are happy to take questions.